Welcome to the Cosmos Corner, where we dive into the vast universe's most intriguing mysteries and recent discoveries. Today, we embark on a thrilling journey beyond our solar system to explore an extraordinary finding that could reshape our understanding of life in the universe. Imagine not one, but two Earth-like planets, each just 6% bigger than our home, nestled in the habitable zone of their star. Fasten your seatbelts as we venture into the depths of space to uncover the secrets of these potentially life-bearing worlds. The James Webb Space Telescope, JWST, was poised to transform our comprehension of exoplanets, planets orbiting stars beyond our own in the Milky Way. It was specifically engineered to detect the faint traces of starlight filtering through an exoplanet's atmosphere, enabling scientists to determine the atmospheric composition. This task is more feasible for larger planets with denser atmospheres, which is where initial efforts were concentrated, utilizing JWST to study giants akin to Jupiter or Neptune. However, the ultimate goal has always been to apply this technique to smaller, Earth-like planets situated within their star's habitable zone, where conditions may be just right for life to emerge. Achieving this, though, requires locating such planets first, a task assigned to the Transiting Exoplanet Survey Satellite, TESS. TESS, along with its precursor Kepler, is dedicated to discovering new exoplanets. Thanks to their efforts, we've now identified over 5,000 confirmed exoplanets, most of which are larger in size. Spotting the smaller exoplanets proves more challenging, and those we do find are not always located within the habitable zone. Of the over 5,000 known exoplanets, merely 60 are considered both small enough to be rocky, Earth-like planets, and situated within their star's habitable zone. This context fueled the excitement surrounding the recent publication by Dransfield and team, which announced the discovery of not just one, but two rocky exoplanets residing in the habitable zone of their star. While the detection of the first planet is quite certain, confidence in the second's discovery is lower. However, pending further observations to confirm its existence, it could represent the smallest habitable zone exoplanet discovered by TESS so far, being only 6% larger than Earth. Before delving deeper into these findings, let's briefly discuss how TESS goes about identifying exoplanets, as there are a few methods for doing so. In a previous video, we explored direct imaging, but there's also the radial velocity, or wobble, method. I covered these techniques in my History of Exoplanets video, which you can find linked in the description below. However, TESS, like Kepler before it, primarily employs the transit method, which involves monitoring stars for periodic decreases in brightness that suggest an exoplanet passing in front of them. The process of detecting exoplanets through their transit across a star, from our vantage point on Earth, significantly favors larger planets or those in close proximity to their stars, or both. This is because such planets obscure more light, leading to a more noticeable reduction in the star's brightness. Consequently, many of the exoplanets identified so far are hot Jupiters, giant planets similar in size to Jupiter, but in much closer orbits around their stars, where temperatures are higher. These planets are simpler to spot due to the substantial dip they cause in stellar brightness. Furthermore, if a planet orbits closely around its star, it completes a revolution in a relatively short period, possibly just a few days, weeks, or months. This means astronomers only need to wait a short while to observe the planet transiting the star again, which helps confirm that the initial brightness dip was indeed caused by a planet rather than stellar variability, such as star spot. This detection method presents challenges when searching for Earth-like planets orbiting Sun-like stars within the habitable zone. For these planets to reside in the habitable zone, they must have orbits similar to Earth's, requiring observers to wait approximately a year to witness and confirm the subtle decrease in the star's brightness again, indicating the presence of a planet. The reason we're able to detect only a minuscule fraction of a percentage drop in a star's brightness when identifying exoplanets is precisely why most of the habitable zone rocky exoplanets discovered to date orbit M-dwarf stars, celestial bodies much cooler and smaller than our Sun, with about 10% of the Sun's mass. Due to their smaller size, planets transiting these stars obscure a relatively larger portion of their light. Additionally, being in the habitable zone of such cooler stars means the planets orbit closer to them, completing their revolutions in just a few weeks or months. This shorter orbital period allows for quicker identification of the regular patterns in the star's light dips caused by these planets. A prime example is the TRAPPIST-1 system, which hosts 7 rocky planets orbiting an M-dwarf star. However, the potential habitability of planets orbiting M-dwarf stars is a subject of ongoing debate. Some argue that M-dwarfs are too active, prone to emitting significant amounts of high-energy radiation through flares, which could irradiate planets, possibly stripping away their atmospheres and rendering them uninhabitable. On the other hand, there are counter-arguments suggesting that under certain conditions, such planets might still be able to support life. The intense flares from M-dwarf stars might not only pose a threat, but could also serve as a catalyst for the biological processes necessary to initiate life. To truly understand which scenario holds true, we must discover and study more planets orbiting M-dwarf stars for their potential habitability. Fortunately, Dransfield and their team have made significant strides in this direction over the past month with the help of TESS. They focused on a star designated TOI 715, located in the direction of the constellation band in the southern hemisphere, and monitored its brightness over a 2-year span. The data from TOI 715, represented by gray dots for individual measurements and a purple line for the average taken over 3-minute intervals, reveal the monitoring effort's depth. Red and green triangles indicate the predicted transit times of 2 exoplanets. At this scale, the transits themselves are indiscernible to the naked eye. It's only by folding the data across the orbital period of the planets, aligning all transits, that a clear signal emerges. This technique highlights how challenging it is to extract meaningful information from the noisy data, as shown by the gray points representing individual observations. By averaging the brightness over 15-minute intervals, the data is represented as pink outlined circles. Dransfield and their colleagues then undertook the task of modeling the transit, determining how variations in the planet's size, mass, and orbital distance could affect the star's light. Several potential models that align with this data are depicted by pink lines. The model that best fits the data for the planet they have confidently identified, TOI 715b, suggests that this planet is 1.5 times the radius of Earth, orbits its star every 19 days, and has an equilibrium temperature 234 Kelvin. 39C. This temperature calculation assumes the planet lacks an atmosphere. The presence of one would imply a warmer climate. The same process was applied to another transit pattern identified by Dransfield and their team, with the gray data points representing raw observations and the green highlighting the averaged data. However, this dataset is considerably noisier, making them less confident about this planet's detection. Nevertheless, model fitting, shown in green lines, was attempted. The most suitable model for this second planet indicates it is 1.66 times the radius of Earth, completing an orbit every 25 days. With an equilibrium temperature of 215 Kelvin or 58 C, the second detection remains less certain, positioning it as a candidate planet pending further confirmation. Without confirmation, it does not yet earn a formal name, retaining a numerical designation instead. The temperatures calculated by Dransfield and their team place both the confirmed planet and the candidate within their star's habitable zone, raising intriguing possibilities about their potential for hosting life. The next step involves considering whether the James Webb Space Telescope JWST could be employed to examine their atmospheres. Specifically, can JWST determine the atmospheric composition, surface temperature, and whether conditions might support life, including the presence of biosignatures indicative of life? To assess the feasibility of such studies, Dransfield and colleagues used the transmissions spectroscopy metric, a gauge of how challenging atmospheric analysis would be. The lower this metric, the more challenging the task. Conversely, a higher metric indicates a more manageable analysis. For JWST to effectively study these atmospheres, this metric should ideally exceed approximately 12. In their findings, the TRAPPIST-1 planets, represented in yellow on their chart, serve as a reference point for this type of analysis. For those eagerly awaiting the JWST data on TRAPPIST-1 with its Earth-like, habitable rocky planets, patience is required. Achieving significant results from JWST is a complex task, especially since the transmission spectroscopy metric for these planets is quite low. This necessitates observing numerous transits, a challenging feat given JWST's packed schedule and the infrequent occurrence of these transits. Quality science demands time, and while anticipation is high for these results, they will not be immediate. In discussions of known rocky planets, attention is drawn to the pink and green data points. The pink points represent TOI 715b, a confirmed planet potentially rocky with a thin atmosphere. This scenario presents a low metric, indicating JWST might need to monitor at least 5 transits to assure any findings. Alternatively, if TOI 715b is a water world with a dense atmosphere, its higher metric suggests a single transit observation could suffice for detection. Yet, without further data, its exact nature remains uncertain. The smaller candidate planet, denoted by green, also awaits more detailed study to understand its potential atmosphere and habitability. The likelihood of the candidate planet having a very thin atmosphere suggests a low metric, leading to the expectation that subsequent studies will primarily focus on TOI 715b. The discoveries made by Transfield and their team are thrilling, marking a pivotal first step towards using JWST to characterize the atmospheres of these promising planets and possibly detecting signs of life biological markers in their atmospheres. They have been observing a relatively nearby star, TOI 715, situated roughly 80 light-years away in the direction of the constellation of Volans in the southern hemisphere. This effort highlights the exciting potential of uncovering life beyond our solar system. Admittedly, while TOI 715b may not easily lend itself to song lyrics, the prospect of discovering life on such a planet is a compelling narrative that captures the imagination. Astronomers have recently made a groundbreaking discovery, locating 2 Earth-like planets orbiting a star not too dissimilar from our Sun. These planets, found in the star's habitable zone, present conditions that could support liquid water on their surfaces, a critical ingredient for life as we know it. This segment delves into how these celestial bodies were detected using advanced telescopes and the significance of their size being only 6% larger than Earth. What makes the habitable zone, often referred to as the Goldilocks zone, so crucial for life? This segment explores the delicate balance of conditions that allow a planet to support liquid water. We'll examine the factors that contribute to a planet being just the right distance from its star, not too hot and not too cold, making these 2 newly discovered planets prime candidates for hosting life. The discovery of these planets sparks endless questions about the potential for life beyond Earth. In this segment, we consider what life could look like on planets that are only slightly larger than our own and how scientists plan to search for signs of life. We'll also touch on the importance of atmosphere, climate, and other factors that could influence the habitability of these worlds. With such a monumental discovery, what comes next? This segment outlines the future missions and technologies that will help us learn more about these Earth-like planets. From next-generation telescopes to space probes, we'll explore the innovative tools that could one day unlock the secrets of these distant worlds and perhaps even find evidence of life. The discovery of 2 Earth-like planets in the habitable zone challenges us to rethink our place in the universe. This final segment reflects on the broader implications of these findings for humanity. How does the possibility of other habitable worlds influence our understanding of life in the cosmos? And what does this mean for the future of space exploration and our quest to find extraterrestrial life? Diving deeper into the scientific methods that led to this astonishing discovery, we uncover the role of the transit method in detecting exoplanets. By observing the slight dimming of a star as a planet passes in front of it, astronomers can infer the presence, size, and orbit of planets around distant stars. This segment reveals the precision and challenges of using this method to find worlds that resemble our own. Water is the elixir of life on Earth, but what role does it play on other planets? This segment explores the significance of finding liquid water in the habitable zone and how it shapes our search for life beyond Earth. We delve into the scientific theories that suggest where water might exist, how it could be detected, and its implications for habitability and the potential for life. How do these newly discovered planets stack up against Earth? This segment offers a comparative analysis of the size, composition, and potential atmospheric conditions of these Earth-like planets. We examine what their 6% larger size means in terms of gravity, atmosphere, and surface conditions, providing a detailed look at how similar or different they could be from our home planet. An atmosphere is crucial for maintaining life-supporting conditions on a planet. This segment delves into the importance of an atmosphere in regulating temperature, protecting against harmful space radiation, and hosting a breathable environment. We'll discuss the methods scientists use to analyze exoplanet atmospheres and what signs they look for as indicators of habitability. Discovering potentially habitable planets ignites the imagination and dreams of visiting these distant worlds. However, interstellar travel presents monumental challenges. This segment explores the vast distances involved, the current limitations of space travel technology, and the innovative ideas that could one day make the journey to these Earth-like planets a reality. Artificial intelligence and machine learning are playing increasingly crucial roles in the discovery and analysis of exoplanets. This segment highlights how these technologies as we continue to refine our methods and technologies. What does the future hold for the discovery of habitable planets? This segment explores the next steps in exoplanet research, including upcoming missions, new telescopes, and the evolving strategies that may one day uncover a planet hosting life. The hunt for exoplanets leverages some of the most advanced technologies in astronomy and space science. This segment explores the cutting-edge tools and techniques, such as spectroscopy and direct imaging, that researchers use to study distant planets. We'll delve into how these technologies allow us to detect atmospheric composition, surface temperatures, and even signs of vegetation or water, providing a clearer picture of these mysterious worlds. While much of our focus has been on planets, moons orbiting these extraterrestrial worlds could also be viable habitats for life. This segment examines the intriguing possibility that moons similar to Jupiter's Europa or Saturn's Enceladus in our solar system could contain subsurface oceans or other conditions conducive to life. We'll discuss the challenges and opportunities in searching for life on exomoons. One of the most exciting aspects of exoplanet research is the search for biosignatures, or signs of life. This segment explains what biosignatures are, including specific gases in an atmosphere that could indicate biological activity and the methods scientists use to detect them. We'll explore how finding a biosignature on an exoplanet would revolutionize our understanding of life in the universe. The exploration of space is no longer the sole domain of government agencies. This segment highlights the growing involvement of private companies in space exploration and their contributions to the search for Earth-like planets. From launching satellites to developing the next generation of space telescopes, we'll discuss how these companies are accelerating our quest to find other worlds. The potential discovery of extraterrestrial life poses profound questions for science, philosophy, and society. This segment contemplates the preparations underway for such a groundbreaking discovery. We'll cover the scientific protocols, the potential impact on human belief systems, and the international efforts to develop guidelines for announcing and responding to evidence of life beyond Earth. As we discover more about exoplanets, Virtual reality technology offers a unique way to explore these distant worlds from the comfort of Earth. Welcome to Blessovia Science TV, where we take you on an exhilarating journey through the cosmos and unravel the mysteries of science. We are excited to offer you the opportunity to become a valued member of our ever-growing community of cosmic enthusiasts and knowledge seekers. Exclusive access to cosmic content. As a member of Blessovia Science TV, you will gain exclusive access to a treasure trove of cosmic content, including documentaries, interviews with leading scientists, space missions updates, and awe-inspiring visualizations of the universe, live Q, and sessions with experts. Your membership will grant you the chance to participate in live Q and sessions with renowned scientists, astronomers, and space explorers. Get your burning questions answered by those who push the boundaries of human knowledge. Embark on a journey that spans the cosmos and join us in unraveling the secrets of the universe. Become a Blessovia Science TV member today, and together we will reach for the stars. Thanks for watching. Subscribe, like, and share. Don't forget to leave your comment.